Hey guys, welcome back. We're going to go into the second part of the AP charge notes now. So Coulomb's law is the first one. That's the only equation in this section. The second main thing that's important is this idea that there is this smallest indivisible amount of charge, which is known as the elementary charge. And so the idea is that an electron or a proton, and very often we cut off this last 0.2 on the 1.6, has a charge magnitude of 1.6 times 10 to the negative 19th coulombs. And that is what all charge is made of. So all charge is going to be made of increments of that amount. So you can't have half an electron, you can't have half a proton. So there's only certain possible values of charge you can have. When there is this smallest indivisible part, that's called quantization. So electric charge is quantized. So you've ever heard of quantum energy? That's what that means also about that. But there's this smallest amount. All right, so a pith ball has a charge of negative 1.28 times 10 to the negative 18th coulombs. How many excess electrons does this represent? So I'm going to write this down, and it is a matter of conversion. And I know that one electron has that charge. And again, it's good practice for you guys to actually put this in your calculators. And so I get 8. So charge is only possible in values of 1.6 times 10 to the negative 19, 3.2 times 10 to the negative 19, 4.8 times 10 to the negative 19, 6.4 times 10 to the negative 19, and on again. So what they'll often ask you, they'll either give you a list of charges and tell you which one of them isn't possible, or ask you which one of them is possible. But it has to be the building blocks of this. And so this was discovered by Robert Millikan, or demonstrated by Robert Millikan, who was an American physicist in the early 1900s. So between 1908 and 1919, he did a series of experiments with this. He won the Nobel Prize for it in physics. And he really demonstrated this with F net equals 0. And he charged drops of oil, and he balanced the electric force that was pushing them up with gravity that was pushing them down. And what he found was that they were clustered, that he had a bunch at a certain value of voltage and then nothing. And there were more at double that voltage, then nothing. And then they were at triple the original voltage, then nothing, and then 4 times the original voltage. And so this told him, and nothing down by 0. And so this told him that that first one was that it had an extra charge of 1. The next one was an extra charge of 2, and from this he deduced what this charge was, that this quantization of charge. So F net equals 0 was all that he needed for that. And then we actually got the mass of an electron from F net equals mv squared over r. So using the second law, they devised what the charge to mass ratio was of the two. Which was Lorentz. Is that? All right, so I'm going to do a little bit of calculations with this. I really want you guys to do this as well on your calculators because, like I said, you often will make mistakes putting it in your calculator. I'm going to have you guys do a FET that's going to deal with this and electric force, and you're going to do a lab where you devise Coulomb's law with F net equals 0. There's two main situations you could look at. You could have a molecular one, and the FET does that. So we're talking about the forces between protons and electrons, or things that got charged. If things did get charged, because a Coulomb is such a huge amount, you're going to have way less than 1. So you're going to have a lot of prefixes usually. If you remember, the prefix micro is 10 to the negative 6th. Nano is 10 to the negative 9th. Pico is 10 to the negative 12th. They wouldn't want you to memorize that, but you have to remember that you always have to get back to your base before you're able to solve the problem, right? So we have to be at whatever the base is. All right, so I'm going to use Coulomb's law, which is K Q1 Q2 over R squared. Again, it could be big Q or little q, very much like it could be big M or little m. I'm going to use this constant, which is on our equation sheet. I'm going to erase this so it's out of my way. And I'm going to leave the sign out of that one. So I'm going to have 6 times 10 to the negative 6 coulombs, 6 times 10 to the negative 6 coulombs divided by 0.025 meters. And again, they're not being mean in these conversions. You wouldn't have things that would have multiple coulombs of charge typically. And now that I say that, I think I have a couple examples coming up where it did. It was from the old honors textbook. And because it diminishes with respect to R squared, your distance is going to be very small. So 2.5 centimeters makes more sense than 2.5 meters. All right, I'm going to put this in my calculator, as I'm hoping you guys are doing as well. And I have 518.4 newtons, and I'm going to say that that is attractive. So I know it's attracting. I don't know what that direction is. You would have to have a free body diagram or some kind of picture to actually be able to tell, right? All right. What about if I need to get the radius? So now I have the force between two protons. I want to know how far they're separated. So I'm going to take my original equation and I'm going to move it around. And then I'm going to plug in what I know. So I'm going to have 9 times 10 to the 9th newtons meters squared coulomb squared. I'm going to have the charge magnitude of a proton squared, and I'm going to have the force they're giving us between it. And I'm going to square root the whole thing. And I got 1.2 times 10 to the negative 10 meters, which seems like a reasonable distance between two things. All right, so I'm hoping you guys will do these as well as I do. I'm just going to set them up. I'm not going to put in the calculator. The answers are in your notes. So consider two clouds of opposite charge equal to 1 times 10 to the 5th coulombs. They're located 7 times 10 to the 11th meters apart. What's the magnitude of the force between them? The equation is at the top of the page. Two protons each have a charge of 1.6 times 10 negative 19th. They're separated by 1.3 times 10 negative 5th. Calculate the force between them. All right, in this case, I'm looking for the charges. I'll scroll this down so it's not as... Maybe not. Well, let me try to get out there. You know? Okay. You can do it. Two equal charges have an electric force of 2.4 times 10 to the negative 6 newtons between them. They are 3.39 meters apart. What are their charges? So the big thing here is that their charges are equal. So I can rewrite this as K Q squared over R squared. So I'm going to get Q by itself. So I'm going to have FE R squared over K square rooted would be Q. So this is 2.4 times 10 to the negative 6th. Yeah, see, like these are ones from your book where they're very far apart. I just want you to be familiar and comfortable with putting in your calculator because there's a lot of little places where you can make mistakes with this. Two electrons each have a charge of negative 1.6 times 10 to the negative 19th. They're separated by 1.2 times 10 to the negative 7 meters. What's the magnitude of force? Again, this is going to be another just plug and chug. But this is useful to do since this is the only equation in this section. And I'm not going to test us on this section. We're going to combine this with circuits. All right, the electric force between two electrons is given. I want to find out how far apart they are. So now I'm going to have to get R by itself. So I have that FE is equal to Q squared R squared. Since they're the same thing, I can make them the same for the charge. And so R, one skip breaks that step. R would be equal to the square root of K Q squared over FE. So we have 9 times 10 to the 9th Newton meter squared Coulomb squared, 1.6 times 10 to the negative 19th Coulomb squared, and put in the force figures. And then the last one, a small quark with an excess of +6 microcoulombs, and I was even nice enough to put in what micro was, is placed 0.12 meters from another quark, which carries a charge of -4.3 microcoulombs. What's the magnitude of the force between the quarks? Is it attractive or repulsive? How many excess electrons are on the negative quark? How many electrons has the positive quark lost? So it would be attractive because one is positive and one is negative. The force would be given by 9 times 10 to the 9 times the charge magnitude. So I'm going to have 6 times 10 to the -6 coulombs. I'm going to have 4.3 times 10 to the -6 coulombs. And I'm going to have 0.12 meters squared. To get how many extra electrons I have, I know that one electron is -1.6 times 10 to the -19. So you might think of this as an equation too, but really it's just a conversion. You're converting from coulombs to electrons or protons. And I would do the same thing with the +6. And again, we usually talk about things in terms of electrons gained or electrons lost, right? Because that's typically in an atom, it is more likely that you're going to get electrons off of it than protons, right? We identify what an atom is by how many protons it has.